Welcome class to this amazing practical video where we will solve some example regarding the concept of diagonalization. Now remember that in the previous video we'll define a diagonalized matrix A by saying that if a square matrix M times M is diagonalized, therefore its eigenvectors V should be such that a matrix P, right, which is equal to the matrix of the eigenvector of A should be invertible. And that leads to the fact that P minus 1AP should be equal to the diagonal matrix of the eigenvalues of A. Right. We also gave you some amazing theorem that need to stick with you along as you are solving problems in linear algebra within the concept of diagonalization. Now, the first theorem says that if an n times n matrix A, right, has an eigenvalue lambda with a multiplicity m, therefore we should yield m distinct eigenvectors for that matrix to be diagonalizable. The second theorem also says that an n times n matrix having n distinct eigenvalue is diagonalizable. And then also at the end of the day, you should also have n basic eigenvector. That is, the dimension of the matrix should be equal to the number of eigenvectors. Now, let's have the first example. Okay, show that A, which is 1, 0, 1, 1, is not diagonalizable. Now, if you remember what we did in the previous video, we showed you the steps how to diagonalize a matrix. The first step was, can you remember? I believe so, was to solve the polynomial equation from this equation, right? So we have that 1 minus lambda 0, 1, 1 minus lambda, determinant which is 1 minus lambda square equals to 0. So what do we have here? Here we have that lambda equals to 1 with a multiplicity of 2, right? I hope you understand, because this is equals to 1 minus lambda times 1 minus lambda, so we have lambda equals to 1 twice. Okay, now after finding the lambdas, we find out the corresponding eigenvectors. Okay, so 2, and we do that by solving the equation IV equals to 0. So what do we have here? We have that lambda equals to 1. So replace it in here. We have 1 minus 1, 0, 1, 1 minus 1, right? If I write it in front of the Gauss echelon, I will have 0, 0, 1, 0. Okay, so here we can see that if I have two variables, my first variable will be x1 and the second will be x2. You realize that x2 is fixed and then x1 is free. So if I say that x1 equals to t, and I will have that from this equation, the first row, I have that s2 equals to 0. So my vector v, right, which is x1, x2, will give me that t0. So I have t1, 0 for t be equal to r. So what do we have here? What we have here, you can quickly see that I can answer this question. So conclusion. So we have proven that I will say that A is not diagonalizable. Why? Because we have a multiplicity of 2, but we just had one eigenvector. And according to the theorem, right? According to the theorem, A cannot be diagonalizable. Perfect. Now, if you have a quick look on another example, you says that diagonalize this matrix 2, 1, 1, 0, 2, 3, 0, minus 1, minus 2. Now, what do you do? The first thing is to solve this equation. A minus lambda I equal to 0, which is equal to 2 minus lambda 1, 1, 0, 2 minus lambda 3, 0, minus 1, minus 2 minus lambda, right? So if you if you have this, you realize that you can do, you can take this as your pivot, right? And then you come to 2 minus lambda, right, times 2 minus lambda minus 2 minus lambda plus 3, right? So this will give you 2 minus lambda, and this will give you lambda square minus 4 plus 3, right? You have 2 minus lambda and lambda square minus 1, which is 2 minus lambda and lambda plus 1 and lambda minus 1. So here I have 3 distinct eigenvalue. So I have that lambda 1 equals to 2, lambda 2 equals to 1, and lambda 3 equals to minus 1. So, and if you remember what we say in the theorem 2, we said that an m times m matrix A having n distinct eigenvalues is diagonalizable. So the n here is the dimension of the matrix, and the n distinct eigenvalues. So in this case, we have a 3 times 3 matrix. So we have a 3 times 3 matrix. We have a 3 times 3 matrix, and we have 3 distinct eigenvalue. So this matrix already, according to this theorem, will be diagonalizable. So the object here is not to derive the eigenvectors of each eigenvalue. By now, you should be able to have that, and then you should be able to then solve the rest of this exercise. However, because of the sake of time, I will give you that the eigenvectors of the eigenvalue equals to 2 will be v1 equals to t, will be v1 equals to t111. So I did that already. T belonging to R, and the one of lambda 2, which is 1, will be v2 equals to s of 011, s belonging to R, and then lambda 3, which is minus 1, will give you that v3 equals to which equal to 013, with gamma and gamma equals to R. So what you can see that is that you have 3 distinct eigenvectors. So you can write your matrix P. Remember, the matrix P is the matrix of the eigenvector of A. So it's 1, 1, 1, 0, 1, 1, 0, 1, 3, right? And then you can check your answer to prove that it is diagonalizable by solving that P minus 1 AP equals to D, the diagonal matrix of the eigenvector, which is equals to 1, 0, 0, 0, 2, 0, 0, 0, minus 1. Yeah, so you have that. Thank you very much, student, for paying attention to this video. And from here, I'm sure that you'll be able to answer the question to find if a matrix is diagonalizable or not. Thank you.